file name. Let me change this to our root directory. We're putting a dot over here. Okay, so I won't be executing this as of now because it's trying to load our file. All right, so now that we have successfully loaded our data, so let's try running this cell over here. Okay, so let me close this and let me zoom in over here. So now what we are going to do is, let's see the shape of our data. So let's see what's the data shape, data dot shape. And now let's see what it would be like. Okay, so as you can see here, we have 5 columns, but the number of rows that we have is 1.8 million. That is approximately 18 lakhs, right? So this is a pretty huge value. So now what we're going to do is, we'll just see how our data is looking like. So we'll see data dot head, and let's see what we need. So as you can see here, we have ID, which is of no use for us. Then we have name. Okay, then this year, I don't think it's of any use for us. Then we have gender and count. Count here represents, how many people have the name Mary, how many people have the name Anna, how many people have the name Emma, Elizabeth, and Minnie. This is over here. Out of this, if you see, right, there are a couple of things that we don't need. We can drop them out. All we need is a name. Okay, and then we also need the gender, because this is going to be our prediction. We are going to predict, we'll give our own custom name, and then we'll see whether the name that is we are giving is a male or a female. Okay, so now what we're going to do is, let's see how many unique values we have. So let me quickly erase this first. Okay, so what I'm going to do is data dot names. So this should give us here name, and then we'll type here as unique. Okay, so this would give me unique values. Okay, so over here I have 93,889 unique names. Okay, so now what we're going to do is, we want to label encode this, right? So we want our female, or which is nothing but F, we want female to be 0 and then male to be 1, or vice versa. So in order to do that, either we can use label encoder, or there's a shortcut method to this. Let me quickly show you how that works. So first off, we'll take our data frame. So it's data, and which column we want to do this for? We want to do this for our gender column, right? So let me pass this and give gender. And now what we're going to do is, okay, we'll take this as type. Okay, this would be obviously in the form of category. And now what we'll do is, this is cat dot codes. Okay, so this is nothing but panda shortcut, do label encoding. Let's try to execute this and see what it would look like. So as you can see here, we have a couple of zeros and ones. This is nothing but, it's representing females with 1 and males with zeros. Okay, so now what we'll do is, we have to update this column. So we'll paste this, and this should be something like this over here. And let me execute this. Okay, so if you want to see how our data would look like now, let me just quickly run this once again. So you'll see here now the values has been label encoded. Okay, so now what we're going to do is, we obviously need to take the unique names, right? And then we'll obviously group it by, right? So what we'll do for this is, we'll take something like data. We'll group this by the names. So group by names. All right. And now what we'll do is, we'll calculate the mean of the genders. We'll reset the index. The reason why we want to reset the index is because, if we don't give the index, then our name over here will become the index, right? So we'll give reset underscore index. All right. So let's give this to a new data frame, and we'll call this as df. Okay, let me execute this now. And let's see how this df would look like. Okay, let me execute this right after this. So as you can see here, it has grouped by names, everything in an ascending order. So this is all in an alphabetical manner. And yeah. And now only thing that I want to work on is this gender. Okay. The reason is because over here, I'm getting a floating point value. I don't want this floating point value. I want to change this to integer value, right? So what I'll do is df gender. This would be nothing but df gender. Then all I'm going to do is as type. I'll just put here as int. So let's now see what this value would look like. Fantastic. We over here have now, ones and zeros, which is nothing but an integer value. Okay. So if you want to see this, so either I can write df, or I can also put as head. Okay. So these are the first 5 values. Okay. So now the way our neural network is going to work, or the recurrent neural network is going to work, is that, I hope you remember these boxes, right? So when I was talking, or when I was explaining this RNN, I was saying that I would be passing around the words. But here in this project or in this program, we won't be passing words over here. We won't be passing like Abha or Abida or Adam. We won't be passing these words. Instead of that, we'll be passing letters. So over here, it's going to be like alphabets. So A, B, it can be any alphabet, it can be Z here. So basically it depends upon whatever the value is coming here. So in order to do that, we have to find number of unique alphabets. So we know how many unique alphabets we have, right? So it's 26. So in order to get these alphabets, what we'll do is, let me first quickly erase this. Erase all drawing. So now we have 26 alphabets. We have to create our own vocabulary. So what I'm going to do is I'm going to import string. So now I need letters, right? So letters, this would be nothing but list of string.ascii. Okay. And if you want to see what this would give me, this would be nothing but the list of alphabets, which are in lower cases. Okay. And now what we'll do is we'll try to create a label encoding, or we have to create a vocabulary, right? So we'll have something like vocab. This would be nothing but I'll be using dictionary. And now what I want is zip. The way I want over here is, for every individual values of this A, B, C, D, I want to label encode this to 0, 1, and whatever the value it is, right? So it would be from 1 to 27, unique numbers, right? So this would be nothing but letters. And then we need something like range 1, 27. So this would give me the matrix from 1 to 26, right? And let's now see what this would look like. So we have vocab, and let me execute this. This should give me a dictionary. Okay. So here we'll convert A to 1. Okay. And then B would be 2, C would be 3, and so on. Z would be 26. And now what we are going to do is we'll just try to create the reverse vocabulary. And the reason is we obviously won't be needing this, but just in case if you want to use, it should be something very similar to this. Let me just copy the exact same thing and paste it over here. So we'll just give it as reverse, right? So it will be R underscore, and here instead of numbers being second, we'll just cut this letters and we'll pass letters over here. And now you'll see if you're trying to decode whatever we have predicted, we can just pass it down like this. Okay, so now what will happen is we need to do something like, all our data, whatever is there, we have to convert them into a lowercase. So, and then once we convert them into a lowercase, we have to encode them into numbers. So whatever I'm saying is this AABAN, right? ABAN. So this AA, obviously first off, we have to convert all of this into a lowercase, this value. And then whatever the equivalent value of A, the numerical value of A, so it's obviously going to be 1. We'll substitute that with this, and it's going to be a list, right? So how do I do that? So for that, I'll write a function. So we'll have def word to number, right? Word to. So now what I'm going to do is I'm going to have for loop for I in range. So this would be nothing but we have to go through the entire shape, right? So df dot shape. This would give me a list, and I just need the first index. Okay. So now what I'm going to do is I'll create one new list sequence. This would be nothing but for letters in df. Obviously we want the names part, and in this we are going to pass the index value. It's going to be I. Let me just give some space here just so that you better understand this. And now what I'm going to do is, I'll have this vocabulary, vocab. See, every time I pass a letter, it will convert it into, this individual letter, it will convert it into a list or the equivalent, numerical representation. It will be letters, and obviously it has to be in lower, so it will be lower. And then we'll just close this bracket here. So now what we are going to do is, before we execute this function, we'll have to append this. So it will be df, and this is going to be names dot I. We'll replace the name in that index with this particular sequence. Okay, so now all we need to do is run this function over here, and yeah, this will take some time. The reason is because we have almost around 18 lakh values. So yeah, this will take some time. Meanwhile, let me just comment this. Okay, so in the next stage, what we are going to do is, let's see how this value over here would look like. So let us now first execute this. All right, so let us now see how our data frame will look like. So let me execute this block now. So as you can see here, our names have been completely changed, or convert it into a list of numbers. But now only issue that we are trying to have is the imbalance in the size of the list. Because when we are trying to have the number of boxes, right, we won't be having variable number of boxes. Okay, so what we're going to do is either we set a value like something like take an average number like 10, 20, or you can take something like, something like you either depend on maximum number or the minimum number of list. But the thing is, if you take the maximum number, then we have to pad a lot of zeros, and this would lead to a loss. So if I reduce the size, this would also decrease the accuracy, right? So what we're going to do is we'll plot this name and gender in the form of a histogram. So let's take here X. This would be df names, and we'll give here as dot values. And then same thing, we'll do it for Y, df gender, and this would be dot values. So what we'll do is we also need a list. Okay, so now as we are going to plot this on a histogram, and what we are going to see in the histogram is just to analyze, this is a graph. We want to analyze, where does the highest number of sequence, or if suppose this is a size, if this is size 8 and this is like 8,000 words or 8,000 names have the size 8, then we can keep our average somewhere near, and then we can also decide, if the number after 10, if not many names have a longer number or the longer length of their name, so we can keep our average somewhere around 9 or 10. Okay, so let's now quickly see how we can do that to get the length of our names. So length X or name length, this would be like list comprehension for I in range 0, df dot shape of 0. And now what we're going to do is we need to find the length. So this would be length X of I. Over here you can either give df or you can also give this X, right? So it would be length of X. Okay, so let me quickly execute this. Okay, so here we're getting an error. Oh yeah, it's not O, it's going to be 0, right? So let me execute this now. Okay, so let me show you how this would look like. Name length, and let me print this off. So as you can see, this is giving me list of names. So there are a huge amount of names. So as you can see, first we had 5, 5, and then 9. So let's now plot this and see how it would look like. Import matplotlib splt. All right, this is perfect. So now what I'm going to do is I have to plot this, right? So all I'm going to do is plt.hist. All right, and now I'm just going to give name length and number of bins. This would be like, let's get 20, okay? And then plt.show. Okay, so what do I find from this graph over here? You see, this is nothing but the length of the names. So 2, 4, 6, 8, 12, all these are the length of the names. And this is nothing but 0, 5,000, 10,000. This is nothing but number of names that have a length 4 or number of names that have the length 6. So as you can see, right, there are around almost 25,000 names whose length is 6. And then as I cross like 10 or as I cross 12, not many names are there whose length is greater than, 12. So what I'm going to do here now is, now we have to pad, right? Now we have to pad the number of zeros. So in order to pad zeros, we have something called as built-in function from Keras. So from Keras, or you can also set as Keras dot preprocessing dot sequence import pad sequence. So let me quickly execute this now. And now what I'm going to do is I'm going to create a new list. So let this be X. This is in lowercase. So pad sequence. And the things that this is going to take is obviously the sequence. We have to give a list of sequence. Okay. And then we'll give something like df.names. And then this is going to be values. And now we want to define the max length. So this is going to be 10. We also have an option of providing where do you want to do the padding. So you can also do it as pre or post. We'll obviously be doing pre. So let's see, how do we do that? This would be nothing but, if you can see this sequence over here. So we have padding is equal to pre. It's by default, right? So
the single most powerful career move for anyone in testing, QA or technical support right now is mastering SQL with AI.
So now what we're going to do is we're going to create our own model. So for that, we'll do from keras.layers, import input layer, and then we have to have embedding layer. Because if you don't have embedding layer, then it would be like each input would be something like 1.9 million, that is 18 lakhs. So it's a pretty huge value to compute. So we don't want that. So that's why we'll use embedding layer. Then we have dense layer, and then we have LSTM. We also, rather than taking this as a sequential model, we'll take it as, feed forward. So what we'll do is from keras.models import model. So now what we are going to do is we'll have to create our input layer. So this will be input is equal to input. And now the shape that we are going to pass over here. So for this shape, so how many columns do we have? We obviously have 10 columns, right? So it's going to be 10. So now what we are going to do is next we are going to have embedding layer. So let's say this is EMB and this would be embedding. So input over here, or the input dimension over here, is nothing but vocab size. We haven't defined this vocab size, so let's quickly do that. So vocab size, this would be nothing but length of vocabularies plus 1. The reason why I'm doing plus 1 is because we also have zeros over here, right? And this would be like vocab size if you want to see. And let me execute this. So we have 27, right? So 26 are the number of alphabets, and 1 is because we have number of zeros. So we'll pass this as vocab size. Okay, and now we are also going to pass output dimension. So output dimension, this is nothing but how many dimensions we want. So now this is going to be 5. All right, and the input for this embedded layer is going to be from INP. Okay, and now we are going to have our first LSTM layer. So it's going to be LSTM1. So this would be LSTM layer. Number of units we have to define here. So units, this is going to be like 32. The units over here does not represent the number of boxes. The units over here represent the A values, right? So now we have to do return sequence, and this is going to be true. And the input for this is going to be from embedded layer. Then we have LSTM second layer, and this is be LSTM units we're going to pass. So number of units that we're going to pass now is 64. And now the input for this is going to be LSTM1. Finally, we have an output layer. So at the end, right, we're going to have a dense layer, right? So dense. So number of units or number of neurons at the end, we are going to have 1. And kind of activation function that I'm going to have here is going to be sigmoid, because we have to predict either it's a male or a female. Okay, so sigmoid, and the input for this is going to be LSTM2. So finally, we have to add this to our model. So I'll give it as my model. This would be model. So now I have to define the inputs. So INPUTS, this is going to be inputs, INP, and outputs, this is going to be out. Okay, so let me quickly execute this now. Okay, so we have this error. Please provide either a shape. Okay, so let's see what's, oh yeah, here I've given it as sparse, right? So it's not going to be sparse, it's going to be shape. So let me quickly execute this once again. Okay, as you can see, we have successfully executed this. And now let's see the model.summary. So as you can see here, first off, we have input layer. Okay, so we can have a number of values, but there will be only 10 features. Okay, that's 10 columns. And then we are going to have, once you go through this embedding layer, then, instead of having 10, instead of having that 1 million or whatever it is, 1.8 million, we'll have just 135 parameters. Okay, similarly over here, and finally at the dense, we have 65 parameters, and then we have 1. The reason why we have 65 here, just for, if you don't know, is because 64 plus 1 bias, and this would give us 65. Okay, so now finally we are going to train our model, but before that we have to compile it. It's going to be my model dot compile. Okay, so we have to find an optimizer. So optimizer, best one that I feel is Adam. Then we have to find the loss. So as we are going to use just 2 predictions, right? Either it's male or female, we'll use binary cross entropy. And then finally the matrix that we want to use here is, this will be accuracy. So let me execute this now. And finally, we are going to compile this. So we'll have history. So this will be model.fit. Okay. And now we're going to pass our values. We're going to give X. We're going to give Y. As you know, X is nothing but the matrix, which has a padding. And Y is nothing but, the other classes. They're telling us either it's ones or zeros. And number of epochs, this is going to be 10. Batch size, as it's a pretty huge data set, we are going to keep a pretty high batch size. So I'll give a batch size here as 256. And then finally, we need validation split. Okay, it's not going to be my model, it's going to be my model, right? So my underscore model. So finally, we're going to have validation split here. So let's give it as 20%. So it's going to be 0.2. All right, so finally, it's the moment of truth. Let us now execute our code. This would take some time to execute. So let's see how this would look like. Okay, so if you can analyze this data over here, so as you can see, right, this validation accuracy has to increase. And we cannot see every time, if our model is overfitting, the accuracy over here will keep on increasing. All right. So the more reliable source over here to see is nothing but validation accuracy. So if validation accuracy is increasing, that means our model is neither overfitting nor underfitting. And you can also see that we have our validation loss, which is kind of decreasing. And over here as well, we can see the validation loss. Over here, we can see the loss of a model is decreasing from 60, then 40, then 39, 39, and 80, 38. So let's now wait for a few more epochs. So we have 4 more to go. Okay, so as you can see here, our validation accuracy has been increasing. So this is a very healthy growth. And even over here, our accuracy of a model is also increasing. Fine. And the loss is decreasing. It's decreased from 60% to 37%. And over here, our validation loss decreased from 42% to 36%. So let us now map this, like whatever values we have received. So in order to map this, we have h. This model over here retrieves us the history function, right? So we'll give hist.history, and let me execute this. Okay, so now what we're going to do is, this is nothing but key value paste. So if I put h, if I give something like accuracy, okay, well, let's plot this. So model.plot, right? So plt.plot. Okay, we'll have accuracy. We'll compare this with respect to accuracy, and then plt.plot. Then we'll have validation accuracy, and we want to show this, right? So plt.show. So as you can see here, okay, so just to give a better analogy, let's execute one of these first. Okay, so the blue line over here represents the accuracy of a model, and then this is nothing but the accuracy of our training data, right, or testing data. So as you can see, our model accuracy isn't decreasing, so it's a very good model and it has trained very well. So now coming down to the moment of truth. So let's now take a random name and see whether it can predict whether the name is true or false. Okay, so we'll give here as test_name. So let's give something like, this will be like name, right? So we'll give name dot lower, and now we are going to pass the name over here. So this would be, let's say, Tom. Okay, so we have to convert this into letters, right? So it will be vocab of I for I in test name, and now we'll give the name here as X test. So this would be nothing but we have to pad the sequence, pad sequence. We'll pass this in a form of a tuple. Then this would be seq. And then we know that we have to pad 10, right? And anyways, we don't have to say whether it's pre or post, because by default it's going to be pre. Fine. So let us now see how our text data would look like. So X test string attribute has, okay. Oh yeah, so I have done a typo over here. It's going to be LOWER. So let me execute this once again. So as you can see here, we have a matrix which has a size of 10. And let's now see what this would predict. So it's the moment of truth. So y.predict, this would be model.predict, and I'm going to pass here as xtest. And let's see what does this predict. So we'll give here as ypred, and yeah, let us execute this. Okay, so we are getting this in a form of an array. So what this tells us, this tells us that, this is like 70% chances that this name is Tom. In order to make this, layman stuff, so what we are going to do is we'll have if ypred. Let me execute this first. So let me go down to another block. So this would be something like if ypred is less than 0.5, then we'll say the name is female, okay? Else print name is masculine or name is, or let it be male, okay? So same thing over here, we'll just keep it as male. So let's now see what this thing predicts. Okay, so this thing predicts male. So let's take another common name. Let's take something like, let's go to Google and see what name can we take. Yeah, we can take up something like Brad Pitt. Okay, so let's execute this, and let's execute this again, and then this. So as you can see here, this is giving me a male name. And let's give a female name over here. Let's give as Mary, and let's see whether this would predict it as male or female. So as you can see here, it's female. Now, as if you have seen the data set, right, it says this is the name from the US kids, right? What will happen if I give an Indian-based name? So let me give an Indian-based name like Priyanka, and let me execute this. It's giving me a female name, right? So this is something pretty astonishing, right? So why do you think it gave me a female name? Well, the reason is because when we are training this model, like RNN, using RNN, right, it's not looking at the name. It doesn't know whether the name is female or not. But as a matter of fact, it is looking at the pattern. Okay. So it might be looking at, if the name ends with so and so, it is a female. If the name starts with this, or if a name have something like this, it means, it's a female or a male. So to give you a better analogy, let's give something like Julia. So let me execute this. This will give me a female, right? So what if I give something like Junaid? This would give it as male. So all it's trying to do is it's trying to see, recognize a pattern. That's why it's taking individual words at the same time. So this is what makes NLP using LSTM very effective. All right, so moving ahead, let's see some of the LSTM's use cases. You see, LSTM is a very popular deep learning algorithm for sequential models. Apple Siri and Google's voice search are some of the real-world examples that have used LSTM. And you won't believe it, LSTM is a success story for those algorithms. So let us now have a look and see how LSTM changed that technology. Okay, so starting off with Apple. In 2003, Apple was the first major tech company to integrate a smart assistant, that is Siri, into an operating system. And the Siri was actually a byproduct of some other company. So Siri was a company's adoption of a standalone app that has been purchased along with the creators who made it. It was somewhere in 2010. The initial reviews about Siri was that it was intense. But over the next few months and years, the users became more impatient with the shortcomings. And all too often, it wrongly interpreted commands. And then, no matter what you do, there was no fix for it. So this is when Apple moved Siri's voice recognition to a neural-based system. Some of the previous technique remain operational, something like, applying hidden Markov models. But most of the time, DNN or deep neural network using LSTM was used. Although people did not find any changes on the outside, but from within, it was a supercharged deep learning model. Speaking about Google's implementation, Google implemented Google Voice Search somewhere in 2009. Google Voice Transcription had initially used something called as Gaussian matrix model. This was nothing but an acoustic model, and this was something considered to be a state-of-the-art speech recognition for almost 30 plus years. But it was in 2012, there was a boom in deep neural network. And when Google implemented deep neural network, that too using multiple layer networks, there was a huge performance gap. But things really improved when recurrent neural network, especially with LSTM RNN, first launched on an Android speech recognition in May 2012. Compared to deep neural network, LSTM RNNs have additional recurrent connections and memory cell that allows them to remember the previous data. Alright, so moving ahead to our last topic of our session, let us now see some of the real-world applications of LSTM RNN networks. First off, we can perform name entity recognition. This is something which we did in our previous demo, right? So what is this name entity recognition? You see, name entity recognition is a subtask of information extraction that seeks to locate and classifies name entity mentioned in an unstructured data. Okay. Next, we have something called as sentiment analysis. Sentiment analysis is a predictive modeling task where model is trained to predict the polarity of a textual data or sentiments like positive, neutral, or negative. Sentiment analysis is performed by various businesses to understand their consumers' behavior towards the product. Then we have machine translation. The task of machine translation consists of reading text in one language and generating text in another language. When neural networks are used for this task, we talk about neural machine translation. Within neural machine translation, an encoder-decoder structure is quite a popular LSTM RNN architecture. Why should we choose deep learning for various tasks? So the big advantage of using deep learning is that we can extract more number of features. And when we have more number of features and when we can work at the same time with huge amount of data, we can perceive an object like a human being does. What I'm trying to say